And first, I would like to talk a little bit of our company, what we do. So WellAI is a digital health platform, and it's been designed for both scientists and commercial use, in particular to empower patients and also to make the work of doctors much more efficient. So you can use it in a commercial application as a simple application on smartphone, just the way you use it Apple Siri or Amazon Alexa. You can just talk to it. So it's essentially every time you have a symptom or a question, it draws from this vast database of medical studies. The WellAI application has many uses. In this particular talk, we will talk about our COVID-19 application, but we will also touch on other topics as well, because as you can imagine, if you have this great knowledge of 30 million plus medical studies, you can apply it very widely. In particular, we managed to create our own database of over 4 million medical concepts, and for this particular COVID-19 tool, we used about 61,000 of them that are particularly related to the COVID-19 and SARS coronavirus problems. Made it available globally at WellAI.health /COVID, as I pointed out here.
First, I want to establish that there's a huge amount of data out there, and genomic data is just one part of it, but think of the textual data, the human knowledge that is out there, that is completely overwhelming us. It's going by as thousands of articles get released every day, and we don't know, actually, maybe there's some treasure that we're missing. The amount of data that we actually use, if you look at the studies and the data that's being used, is only about, 2/1000% of available data that actually is being comprehended. And that's a big problem, because the data tsunami is just going to get worse every year or every month. Somebody realized that you can actually fit mathematical models on a language. And so in the English language, what was found out amazingly is that mathematical vectors actually keep a lot of the properties of the language the way we use it. So if you take a vector, mathematical vector for king, subtract the vector from queen, using simple, kind of algebra, it's actually, the difference is the same as vectors between men and a woman. And so similar kind of semantic relationships hold in math between capitals and cities. So you have USA, Washington, Russia, Moscow, Japan, Tokyo, and Turkey, Ankara. It's actually going to be similar. So every medical concept, every gene, every nucleic acid, every protein gets assigned this 300-dimensional vector from the studies. But even those simple models understand that petroleum, oil and gas, and country, town, and village have a similar kind of hierarchical relationship. And then there are much more complex models. So you'll use Google or Google Translate, and whatever. These models are actually far more complex, but they use the same underlying idea. Words are encoded as vectors, and then various math is done with them, because remember, we find that different concepts in the language actually hold, the mathematical relationships hold. And so there are so-called transformer models. These are really complex models that are used, but the core is the same. Language can be expressed as math, and we can help tackle a problem. Those three things you have to remember. There's no intelligence in artificial intelligence. There's no learning in deep learning, and there's no neural networks. Why? How can I prove this? I'm just going to show. This is an interesting example. It's not from language. It's actually from computer vision, but the models employed are very similar. See, on the left, we have a neural network that recognized the panda, right? And it recognized the panda with almost 60% confidence, not very high. But what turns out that you can actually take these neural networks and you can apply just very little noise, but in a very targeted way, using some calculus to trick the model. All of a sudden, picture on the right also has a panda, right? For any human, it's clear that it's a panda, yet the model with almost 100% confidence thinks it's a gibbon. The point about from this example and from many other such examples, they're called adversarial examples, is that neural networks or artificial intelligence or deep learning, they're not really learning, right? Because learning is a generalization of concepts. You have to generalize to learn. That's what humans do. I just want to say that when you hear this is snake oil, when you hear a lot of this nonsense that what AI can do, how it's intelligent, how it will replace humans, it is not going to happen. This is a simple example. Now, of course, you can build more complicated neural networks to cover for this example, but they get much more complicated. And the point is, just the fact that this example exists shows you already that there's no generalization. Whereas I think most models that we apply right now in the scientific world, they actually look at it as not object-oriented, but like a linear program. And so there's very linear relationships, and almost everywhere we try to fit these kinds of models. Why? Because that's kind of really what our math allows. The math right now cannot deal with the amount of data, right? And I will say that there's an example from chemistry that we took as inspiration. There was an article in Nature where they used mathematical models of language, very simple ones, to actually predict qualities of materials. You'll see that what we've done is we took hundreds of thousands of studies that you cannot possibly read, and we use these models to categorize them. So, and to really clusterize the concepts. In other words, what we've done is we absorbed lots of literature that you cannot possibly read, and we digested these relationships, complex relationships between entities, and we're showing you here what these relationships are. And you can take any number of entities, put them as your given, and then see what are other relationships that it suggests. And more likely than not, some will be obvious to you, but some will not be. And we believe that in the long run, using models like this is what can help us deal with this immense amount of data. Because now we're not just starting anew, we're actually using lots of research that was done already. We're extracting all these relationships, and all of a sudden we can create a much more robust model because we know the entities that are related. And so to summarize, mathematical models of language, in our opinion, are some of the most important scientific tools for 21st century. Why? Because the only way we get knowledge is we can only look at humans. Math models will not give us knowledge. But humans put out research every day, but yet very few people can read this research because there's so much of it. And we believe that these kinds of models can help you, whatever field you work in, you can go in and actually find related concepts, find more and more suggestions about what to do. And we're going to put out a more general model too for scientists, not just for COVID. And if you work in other fields where it's interesting for you to analyze literature this way, we're always looking for new interesting collaborations. You can ping us there.